Hi, gang, Math 6610, diving into another chi-square test, and this one's called Goodness of Fit test. Now, let's reflect. The chi-square test of independence uh, examines the relationship between two categorical variables, and these categorical variables are sample data. So that's a distinct difference between the chi-square goodness of fit and the chi-square test of independence. I will tell you that in isolation, again, let me pump the brakes here just a second, circle back. When I put together the 6610 and 6620 class, I am preparing you to perform quantitative research uh, in the master's thesis component. I can't imagine a research question, a research proposal being submitted to me and me approving it that only used a chi-square goodness of fit test. However, there could be some introductory research questions or some kind of subplots that you may want to examine where it may be appropriate to use a chi-square goodness of fit test. Now, so the example here that I'm going to use, and I think it illustrates the chi-square goodness of fit test perfectly. In 2020, they were actually turned out, I think there were about 445,000 students who took about 850,000 AP exams. My daughters were two of those. I think Sadie's taken 5 AP courses and Bailey's taken 4. And they've scored 5s on most of them, so they've done really well. But their lowest one score was in statistics, and it wasn't even really that low. But it was they didn't get a 5 on it. I don't know what that says, considering my profession, me as a dad. But anyway, so the nature of a chi-square goodness of fit test is you start out with a statement about the population. So our population here is all students who took an AP uh, score, specifically an AP statistics test, and this describes the distribution for the population. 25% scored a 1, 17% scored a 2, and so on. Now, an administrator is curious if their students who took the AP statistics test compares to the national average, the national distribution. So they sampled 392 students, and they have a distribution for their school district. And again, this is a feature of the chi-square goodness of fit test: a statement about your population and sample data. You're comparing your sample data to a population distribution. It's really a lot like, I know I'm going to regret getting on this tangent because I'm afraid it'll start confusion, or at least motivate some confusion, but it's a lot like just a simple t-test. We make a claim, right? A claim that maybe that the mean ACT is for a particular school district is 24, and we compare that maybe we aren't 24 after all. We've made a statement about our population, and we use sample data to test this. We make a statement about our population, we use sample data to test this. So let's scratch that out because that's not what we're doing, but it's just a way of thinking about it. Now, the chi-square test statistic is calculated the same way with a couple of caveats. A couple of differences for the degree of freedom and the p-value. So the very first thing, again, in calculating the test statistic, we have an observed uh, vector, a row vector in this case, and we have an expected vector. Well, the observed vector is always just going to be our the data that we have collected: 71, 86, 74, and so on. So our expected is going to be what we expect under the null hypothesis. And I'll present the null hypothesis and all that in just a second. So think about it. Of these 392 students, how many would we expect to get a 1 if this distribution holds true? Well, 25% of 392, which is 98. How many would we expect to get A2? Well, 17%. 0.17 times 392 is 66.64. Once we have our observed vector and our expected vector, then the calculation of the test statistic is just your observed minus your expected squared over your expected. So just sum all that up. Now, I'll make those calculations in R. So let me bump out of here, and I've already got this in R. So this is the way we carry out a chi-square goodness of fit test in R. First thing I would do is I would name, in this case, it kind of made sense to me that I named it AP Stats, and I put in the frequencies. So these are frequencies, right? 71 students from the school district earned a 1, 86 earned a 2, and so on. The next thing I do is I use this chi-square.test command in R. Now, there's a lot under the hood for the chi-square test, as we saw with the test of independence. But in its simplest form, we can use this command for the chi-square goodness of fit. So whatever we name our counts from our sample data goes first. And then the P, which is the probabilities, percentages of each corresponding score. So 25%, 17%, because this was the statement about the population. Run the model, and you can see that we get a test statistic of 19.6, degrees of freedom equal to 4. Now, in contrast to the test of independence, where the degrees of freedom were the number of rows minus 1 times the number of columns minus 1, the degrees of freedom is just the number of groups minus 1. So we have 5 scores, minus 1 gives us 4. Our p-value is statistically significant at the 0.01 level. Now, what does this mean? Well, it doesn't mean anything if you don't understand the null and alternative hypotheses. The null hypothesis in the chi-square chi-square goodness of fit test is that the percentages for the population are met. They're true. I always hesitate to use that word true, but these are the populations, right? The alternative hypothesis is that at least one percentage is different. So by rejecting the null, we conclude that this statement is, again, pump the brakes, it's not true. We conclude that that statement is more believable. So we accept it. We reject this statement because, again, H sub A is more believable based on our sample data. Now, we can dive into the weeds a little bit and run model $expected, and we get our expected values. We saw that earlier. We calculated those by hand. And what's most important, considering our decision, at least one percentage is different. Well, which one is it that's different? Well, the standardized residuals allow us to make a statement about that. So just like before, I have tunnel vision on standardized residuals greater than 1.96 or lower than negative 1.96. And again, why 1.96? Well, when we standardize something, we start living in the z-score world, right? And we know in a normal distribution that 95% of our distribution is between negative 1.96 and positive 1.96. Now, we typically eyeball it at negative 2 and positive 2, right? But so we know that the area in the tails of the distribution of z-score is the standard normal distribution. 0.025 in the right tail, 0.025 in the left tail, are above 1.96 and below negative 1.96. So, tunnel vision. There's one that concerns me. So, what does that tell us about the school district? Well, I've written it out here. I said the observed number of students who scored a 1 is 3.15 standard errors below what we would expect under the null hypothesis. So less students scored a 1 than we would have expected if the nationwide distribution applied to the school district. Compare that to students who scored a 2. The observed number of students who scored a 2 is 2.6 standard errors above what we'd expect under the null hypothesis. The only other one that kind of presents a red flag, it's not really a red flag, it's just describing your sample data. It's describing the distribution of scores at the school district compared to the national scores, is 2.38. So there were more students who scored a 5 at this school district than we would have expected if we had followed the national distribution. So that's a good thing. Is it a good thing that less students scored a 1? Well, yeah, because a 1 is obviously the lowest score. And of course, just interpret this: more students scored a 2 than we would have expected. We really don't deviate a lot of the scores of 3 and 4. The school district doesn't deviate a lot from the national AP score distribution. Now, let's pump the brakes a little bit and circle back. Every test that I've presented so far, we've discussed effect sizes, and I'm not going to get into effect sizes for chi-square distribution because we really dive into categorical variables later in probably in 6620. But what we use for effect sizes is something called odds ratios, and we can calculate confidence intervals for odds ratios. But I'm not going to present that yet. So again, the purpose of lesson 1 is kind of to reflect, review things that I hope you learned in your undergraduate class, statistics class. So I doubt effect sizes, odds ratios were covered. All right, that's all I have, I believe. I don't believe there's anything else. Yeah, that's it. Take care.